Over to you.
Okay, cool. Yeah, I'm pleased to meet you guys. I know I've been chatting to many of you over Telegram groups, but I'm finally happy that I'm getting some FaceTime with you guys. Uh, yeah, so today I just wanted to talk about some topics in linear algebra. I just quickly scanned through all the videos that guys have posted before. I thought what was missing in those videos is the context around linear algebra, right? I understand, I mean, unless you have worked on that, it's very, very hard to give the right context, right? So I thought that is where I can help, right? Provide some context and provide some motivation for linear algebra, right? I just wanted this session to be like that, right? So just introducing some basic concepts and also giving some intuition, right? And why this is sort of important and where these things are actually applicable, right? So I just wanted to dedicate this session for that. Before that, can you guys see my screen or just me?
Just you.
Just you.
Okay. This is your screen. Open system preferences. So, oh, it is saying that I have to quit and join again because uh, the system preferences would not take effect for sharing the screen.
All
Just
right.
once again.
Sure, sure.
Okay.
Yeah, we can see your screen.
Oh,
Yeah,
still? Okay, let me just quit.
yeah. I can see inbox, Telegram, web.
Oh, it's working now. Cool, cool.
Yeah,
That's good.
yeah. Google Keep.
Okay, that sounds good. Google Keep. Where did you see? Are you seeing the other screen? Which screen are you seeing?
I see inbox, Google Keep, Telegram, web.
Oh, okay, okay. I'm sharing the wrong screen then. Hold on. Hmm. Oh, can I stop share? Then I'll share the other screen. This one, desktop too. Okay, now you should see, right?
Wait. It
So now you're
says
seeing the iPad screen.
yes, I do. I see Google. I
Okay.
see. Yes, I do.
Okay, so
Mm.
can you see the
Yes, yes.
written part? Cool. Sounds good. Okay, then I think we're all set, but probably we are 12 minutes late. Anyway, we got started. That's good. Let me start off with a question. How many of you guys have heard of this?
At least I haven't.
Okay. Series. Does anybody know what series is? Okay. Let's just Google it. Okay. So Sirius, if you look at it, right, it's the first asteroid discovered in January 1801 by somebody that's not very important. Later it was classified as an asteroid and then it was a dwarf planet, blah, blah, blah. So basically this is, we all are aware of the asteroid belt, right? It's somewhere between Mars and Jupiter, right? And this is the first planet that was actually discovered, or the asteroid that was actually discovered in this asteroid belt. Uh, so that is what series is, right? So there is some context to this and linear algebra. We will slowly figure it out, right? The next one I wanted to talk about is, how many of you guys have heard of this guy? Carl Friedrich Gauss.
Of course, normal
Of course,
distribution.
right? Yeah, yeah, exactly. Let's
And I think Gauss law in electrical theory, if I'm right, that was
yeah.
famous to class 12. Something to
Okay,
do with flux, if I'm right.
sure. So let me highlight about this guy. So he is considered to be one of the greatest mathematicians that ever lived. Okay. When we read about these big guys, right, like Gauss or Einstein or whatever, right, we know that they are big, but I don't think we really understand the magnitude of how big they are. Okay, so one of the examples that somebody gave me was that when you look at all these big guys, assume that one day you decided to become to play tennis, right? And then you became a Roger Federer, okay? And then once you have reached that level, you decide that you don't want to do tennis, but then you want to do basketball. And then start playing basketball, you become a Michael Jordan. And then you drop basketball, start playing chess, and then you become who are that guy is? Magnus Carlsen, right? Yeah. What's his name? Yeah, Magnus Carlsen. Yeah, whatever that guy is, right? Yeah. So that's how big these guys are, right? So that kind of gives us a context of like now what these big guys have done and how much their contributions have impacted us, right? And the reason I'm bringing Gauss is that there is some connection between Gauss and series and linear algebra, right? So this kind of gives you a context on like where we stand. We are not just reading something on the book, right? So these are like strong historical roots there, and you will realize like how deeply these techniques have impacted us. So I'm just building some intuition there. So let's go look at this guy's wiki page, right? So typically, if you name a scientist, they'll be known for something, right? Let's go look at the list for this guy. If you look at this, the known for itself is a wiki page. You go click on that wiki page, right? Now you will see the number of contributions to each of those. You see, we just came up with like one or two names, right? But if you look at linear algebra, there are a ton of things in linear algebra. If you look at differential geometry, ton of things. Number theory, huge. So basically, this is tennis, this is basketball, and this is chess. You name it, right? Statistics, everything, right? So we are now standing on the shoulder of these giants, and when we hear about these names, that's why I think it's important to pay more attention to what they have done, because those guys' work have deeply impacted us in many ways, and which we don't even realize, we take for granted. Okay. So we have done some two orthogonal things. Now I have to connect them, right? So I think it's looking like the first 15 minutes of Jigger than the double X, but you will see the connection now, right? Series solver, right? Uh, so this is the final connection, okay? So series solver, right? So this is a non-linear least square solver. Basically, this is developed by Google, and this is the C++ library, which is heavily used within Google, and many robotics groups also use it, right? I just want you guys to read this one. I can read it loud, okay? While there's some debate as to who invented the method of least squares, there is no questioning the fact that it was Carl Friedrich Gauss who brought it to the attention of the world. Using just 22 observations of the newly discovered asteroid series, Gauss used the method of least squares to correctly predict when and where the asteroid will emerge from behind the sun. We named our solver after Ceres to celebrate the seminal event in the history of astronomy, statistics, and optimization, right? So that's the connection between Ceres and Gauss, right? And now, this is where all the real stuff ends. So I'm going to use some fiction on top of this to simplify what Gauss did, okay? This is my own interpretation, but it's not too far from what Gauss did, at least in terms of the inspiration, right? But the actual technique will vary. So this is where this is how I want to set this up, right? So there is Ceres, there is Gauss, and there are two key points, right? He made 22 observations, right? And how is this all tying together, right? Let's see how he did it. Okay. So let us say that Gauss made some observations. Okay. These are the points that he observed. Okay. And then this is where the sun is. So what he wants to predict is where is this series going to be, right? And then he wants to point there, and then he figure it out, right? So I'm going to make some simplifications here. You can see that these points are actually following a curve, right? Right. And let us say, for example, again, this is my simplification just to give some motivation. Let us say that these points are actually following a quadratic curve, right? now what do we have? So Gauss has some observations, some points, right? So those points are, say, let's say this is x-axis and this is y-axis, right? He made some observations, right? X and y, right? That's what he did, right? And he's making, this is the data, right? And there is some assumption that he's making that it's a quadratic. This is my assumption here. So some assumption on the model. In our case, we are saying that it's quadratic, right? But actually this model comes from the Kepler's laws of planetary motion and so many other things, right? And what Gauss ultimately ended up using was an eighth order polynomial. So for this discussion, I'm just simplifying it. Let's say it's quadratic, right? So the problem is trying to solve here is that, but this quadratic equation, we know it's a quadratic curve, right? So let's take a simple quadratic curve like ax square plus bx plus c is equal to 0. This is a simple quadratic curve, right? So depending on the choice of a, b, and c, you get different quadratic curves, right? So we are all aware of that, right? So if you're for one choice of
Sorry, is that a curve or is that an equation, the one that you have?
the equation will result in the curve, right? So if I
No,
choose
shouldn't that be
ax,
y is equal to ax square plus bx plus c instead of equal to
yeah,
0?
sorry, yeah, you're right, it should be y, you're right. Okay, let's
Yep.
let's just do this, right? Let's
Right.
simple equation y is equal to ax square plus bx plus c. Okay,
Mm.
uh, so if so what we don't know is the unknowns, right? Sorry, what are the parameters of this curve? It's a, b, and c. So given a choice of a, b, and c, it results in a unique quadratic curve, right? That's what it is, right? So the problem here is that you know there are some points which is the data, right? So data in this case is nothing but the x's, right? Right?
And
Generally
and
speaking, right?
y is too, isn't it?
Yes, y's too. X and y are the data, right? Ax,
Mm.
I think let me put it ax square. mm, Let me put it this way: ax square plus. Actually, if you look at a 2D quadratic curve, it's actually more. I don't think this is the exact functional form. It should also involve xy terms. Let's just
Mm.
simplify it for now. Bx plus c minus y is equal to 0. Okay, let's say this is the simplified equation for this curve. So the data here is x and y, right? This is what we have measured, which this is what we have observed through our experiments, right? And we are assuming this quadratic form because we have some domain knowledge about the data, right? In this case, it's a quadratic curve, but the actual orbital mechanics says that it's an eighth order polynomial, right? So given these two things, uh, can we find the parameters A, B, and C? You see my point? So given these parameters A, B, and C, now I can plug any X I want, right? And then I figure out this blue thing. You see my point? The X here is nothing but the time, right? Because the planet is orbiting. So X here is simply the time. Given the time, I want to know where the location is, right? So now we can see that this beautifully fits into the realm of linear algebra because you have some data which can be arranged in the form of a matrix, right? And you have unknown parameters A, B, and C, and then you have 0, 0, 0, whatever, right? So now this fits into the form A x is equal to 0. And this sort of gives you an indication of like how a linear algebra is applicable here, right? So whenever, broadly speaking, so where is linear algebra helpful, right? One is that you have some data that you observe through experimentation or something else. And then you have some knowledge about the underlying process, right? So underlying function that's actually generating the data, which can be parameterized, okay? So in this case, it's a quadratic example, right? Quadratic equation. And And given these two things, you're actually doing a parameter search, right? Because A, B, and C. So A is an element of like minus infinity to plus infinity, right? Same thing B and C, right? So they extend from minus infinity to plus infinity, right? So out of this range, what is the best set of parameters that describes this data? That's what you're trying to figure out, right? So you can see this linear solving this linear system of equations as a parameter search problem. So this is where linear algebra fits in. Okay, is this clear, guys? Any
Question
questions? Yeah.
is uh, in this particular case, is there an optimization that is happening here, or are we going to get a solution to ABC? A deterministic solution to ABC.
We will get a solution to ABC.
Right. So there's no optimization happening here, right?
What do you mean by optimization here?
When I say optimization, I'm talking of the use of least squares or anything of that sort.
So
Because here we are, the reason I'm asking this is, what if the data don't quite fit into, exactly fit into that quadratic shape? Here you're assuming that it'll fit into the quadratic shape, isn't it?
that's coming from domain knowledge. So let's say that the data is like spread out like this, right? Not exactly on the curve.
Exactly. Yeah, let's say it's that way,
So
but I still believe it's close to quadratic. Let's say. How does linear
yeah,
algebra
it'll
help
be
there?
close to quadratic. So it'll help you find the least square solution. Which mean, what do you mean by least squares? Least squares is basically the sum of residual errors that will get reduced.
Hmm. But
So
would we
if you fit a
still
curve,
frame the problem the way you have framed it in that case, or would it be framed a little differently?
it is the same thing. It is the same thing,
Okay. All
right?
right.
So I'm framing this problem because I know something about the underlying data. That's what it is, right?
Hmm.
And I know that the data is noisy, right? So we are making, you're assuming like these are perfect observations. Observations are not perfect, right? So those are going to be noisy. And even in this Gauss's example, he predicted the location of series within half a degree error. That's what he claimed. That's what he did. So there will be an error, right? And that error is based on uh, your observations data. That's one of the main things. And if you go deeper into linear algebra, you will realize that it also depends on the properties of the matrix also. Because whenever there's an inverse involved, if the determinant is close to zero, then our techniques will not work really, really well. So there are like multiple factors there. So it of course depends on the quality of the data and how well conditioned the matrix is. But I think those are like advanced concepts. I think this is good enough for a motivation uh, example. Okay.
So, is the domain knowledge and the underlying understanding that, hey, this domain knowledge fits actually a quadratic model, right? Is that a precursor to
Yes,
forming the
yes.
problem?
You need to know. Yes, you need to know what the underlying model is, right? Right. So if I say that this is a cubic equation, right? Well, how does a cubic equation look like? It looks like this, right? Oh, no, no, there will be like two dips. Sorry, I've drawn too many dips here, right? I'll not be one dip, there'll be two dips in a cubic equation, right? If I assume that this is a cubic equation, then I'll have more parameters to estimate. Least squares will still find the best fit that minimizes the error, but that will not capture the underlying process well.
Okay.
You see my point? At the end of the day, it's
Yeah,
just
yeah.
finding a solution, right? So if you incorrectly parameterize the data, right, then of course your predictions are going to be wrong. You see my point?
Yeah, yeah. Okay.
Right?
So what you're saying is, I mean, if I didn't know the
Mhm.
orbital mechanics behind it,
Yes.
then I could have come up with some random expression. Least
Yeah.
squares will still give me a solution,
Yes.
but I mean, it may be senseless. It may not be able
Yeah.
to predict where the
Exactly.
asteroid would be, right?
Yeah.
Okay.
So at the end of the day, it's computing X given A, right? So
Mm.
you are telling the nature of X. So
Mm.
this X is basically ABC in our case, right? This, you're telling the nature of X and you're saying that, okay, this is the nature of X, find me, right? And
Mm.
least squares will just give you that. But if you mischaracterize the nature of X, then of course it's going to be wrong,
Mm.
right?
All right. Yeah, got it.
Cool. Okay. So this is an example just using curves. So I thought let's get to more real world stuff here. This is also real world, but like how we do the modeling here. I simplified the modeling part. Okay. Uh, I just want to quickly touch upon some computer vision examples because this is what I know the best. Okay. So let's say that we have a camera, right? Let's say that it's observing a chair. Okay. So we know that let's say that 3D points, we know that the world this is in some coordinate frame and this is a 3D world, right? So the camera is capturing an image of the same chair, right? And you have some points here, the corresponding points here, but this is a 2D image, right? So if you can look at camera as a mathematical function, right? Which takes X, Y, Z, the world coordinates as inputs, okay? And converts them to image coordinates. Does it make sense? Mathematically, the camera is a function which converts 3D points to 2D points. That's how it is, right? So now you can see the inspiration here, right? So if this is a function, right, it has some parametric form, right? Can I estimate this parametric form? Does that make sense? Does this argument make
And
sense, guys?
my only question would be, here the assumption is that transformation is linear, isn't it? That's the assumption.
Yes. Yeah. I'm just taking a very simplified camera model. Let's say that
But
this is a
is it
pinhole
but is
camera.
it linear in general? Cameras?
Pinhole camera model is in here. That's why I'm suffixing it. It's a pinhole camera model. So there are like multiple levels of modeling it, right? So you basically start off with the pinhole model, and then you add some distortion to it. That's where the nonlinear part comes up. So let's just make it very simplified,
Linear.
right? So I'm
All
just
right.
giving you, yeah, I'm just giving you an example to see how we can do the modeling. Okay, just to develop some intuition. So here we just drew points on the curve, and then it's very easy to say, right? But in real engineering, how does this happen, right? I'm just trying to give some intuition on that. Okay. Uh, so a quick question for you guys, right? What the camera consists of like imaging sensor and some lens, right? So just in terms of like intuitive physics, what could be let's say if I model the camera as a mathematical function, what could be a parameter to that model? Just some guesses.
Can you explain that question again?
Actually, the camera will sense the pixels and converts in equivalent voltage.
Sorry, can you come again?
Actually, camera sensor, what it does is it collects the pixels and converts it into equivalent voltage and does some processing.
No, I'm just trying to capture the relationship between 3D points and 2D points, right? And this function is helping us capture that, right? So a camera consists of an imaging sensor and a lens, right? You can just oversimplify the components here, right?
With the
So
curvature, focal length also.
good, that's a good point. Yes. So how does the focal length impact the image? Can somebody explain that?
Uh, Smaller focal length will result in a larger image. Is that right? I'm just trying to recollect.
Good. Yeah. Good
Right.
intuition. So when the focal length becomes shorter and shorter, you will have a wider field of view, right? As you zoom in, right, in your DSLRs, right? So people who have used DSLRs, so what is actually happening? You're actually increasing the focal length, right? So you're able to zoom in since the field of view is zooming in, right, the objects look magnified, right? So the focal length is an important factor in modeling the camera, right? So this mathematical function definitely takes focal length as input. Okay, let us just stop with focal length for now, right? Just to build the intuition, right? So now let's say I want to mathematically model this camera. Now, if I want to translate this into a linear algebra problem, I said there are the two things, right? One is the data, right? Next is the mathematical model, right? And then finally, you applied some linear algebra techniques to estimate the model, right? So in this case, if I want to estimate this focal length, right? I can do controlled experiments, right? To know the 3D coordinates of these points, right? So typically what we do is we take a checkerboard pattern of a known dimensions and then point it before the camera. So we exactly know what the 3D coordinates of the corners are, right? So that gives me the 3D data. Okay. And then since I have captured an image, I can estimate the corners also in the image, right? So that gives me the 2D data. You see your point? So that's how I generate both the 2D data and the 3D data required for this model estimation, right? And then I
Sorry,
develop
just to be
mathematical.
sure, just to be sure.
Yeah. Hmm?
So from 3D to 2D,
Mm-hmm.
I mean, I don't want to get into the specifics, but do we use, I mean, what do we typically do to get to the 2D data? Because the function is supposed to do that, isn't it? No?
When you capture an image, right? The camera is giving the data. So the physically the camera is telling you what the 2D coordinates are.
Okay.
Right?
All right.
So
Okay.
I'm replacing that physical process with my mathematical function, right? So now I'm trying to estimate what could that function be. You see my point?
Right. Okay, I get it. Okay.
Right.
So it's like, so
So
what you're
now you
saying
can see.
is, I have a camera with me. I'm taking a bunch of pictures. I know
Yes.
what pictures I'm taking, so I know in 3D space what where those points are. I've also taken a photograph, so which means I know in 2D space, how it gets reflected on the camera, and that becomes my data set to figure out what exactly is the camera doing behind the scenes, right?
Exactly. Right.
Right.
So so now I'm not going to the details of this model, right? So I'm just telling you that we have identified that focal length is a parameter in that model, right? There are a couple of other parameters also, but yeah, let's not get too much into computer vision. But then you can see that it's kind of fitting into this realm of linear algebra, right? I can do controlled experiments to get the data. I have domain knowledge, right? I know the focal length is going to impact the image. I can build a model out of that. So if I have these two, now I can estimate the parameters of the model, which is nothing but the focal length. You see? So that's how, this is how many engineering problems are formulated. If you step outside the world of software engineering, you will see that pretty much any domain you get into, right? You will see this repeating over and over and over again, right? And that's why linear algebra is like so powerful, right? So if you're from a computer vision background, you will be more well versed with like camera models and stuff, right? But then if you go to a different domain, the domain knowledge will be different, and you'll have different set of models to work with. But then the underlying techniques are still the same. So that's why linear algebra has so many applications. It has applications cartography, it has complete applications robotics, computer vision, like any field you name, operations research, right? So that's why I think this is such an important tool for an engineer, right? And yeah, I think that I've given you guys some intuition about linear algebra. Do you have any questions on this?
I'm good.
You're good?
Yes, at least I'm good. I don't know about the audience, the rest of the audience, but I'm good.
Other folks, no questions? Okay, cool. Let me just save this.
If I have questions, I'll stop you then and there. That's how I do it.
Sure,
Is it okay? Is it okay?
Yes. Yeah, sounds good. Still one. Yeah, I've actually not started it on the today's content. I'm just giving. I've spent like how many minutes on the motivation? Wow, it's been half an hour purely on the motivation part. But I hope this actually motivates people. That's the whole point. Okay, so what is our content for today? Intuitive explanation of eigenvectors. Okay, so we have been discussing a lot about eigenvectors, right? Now I'm going to switch a little bit and then go back to practical examples once again. Some math now, okay? Let's start with the eigen equation.
So was this one of those Germans? Just like
Eigen,
sounds like
probably, yeah.
German word, right? I suppose.
Yeah. I've not read much about eigen. Yeah, it's
Okay.
true. So this is the eigen equation. I hope you guys are familiar with this, right? AV is equal to lambda V, right? This is not strictly AX is equal to 0, but let's start with this, right? Okay. So let's just dissect this equation. What is A here? Can somebody tell what is this?
A matrix.
Good. What is V?
A vector.
What is lambda?
Scalar. Of course, a
And
vector.
V, same vector. That's the point.
Right.
It's the same vector, right? So let's just now focus on the left-hand side of the equation, okay? A, B, okay? I'm going to cook some examples here. Let's say A is equal to 2, 0, 0, 3. Okay. I'm going to choose a point, sorry, vector 1, 1, 1, 1. This is the vector V, right? Let's now do AV. 2, right? 2 times
2
1 plus 0 times 1.
3.
Right? So AV is equal to 2, 3. Okay? Let's mark what is 2 here. Let's say this is 2. Let's say this is 3. 2, 3 is somewhere here. You guys agree?
Yep. Certainly not a scalar multiple, right?
Exactly, right?
Right.
So the bottom line here is that when you are multiplying a vector, multiplying by a vector by a matrix, right? What is happening to the vector? The vector is actually changing its direction, right? The vector is actually changing its direction. But what does the eigen equation say?
Arvind, is it you or?
Okay.
No.
No, it's not from me.
Wait, I think it's Saurati, is it? Wait,
Okay. Sorry, guys.
give me a moment. I'll just mute.
Yeah. Now
I
it's
think
gone. Now it's gone.
Okay, cool. Sorry.
Now it's gone. Okay. Okay. So what does the eigen equation say? It says if you transform a vector by a matrix, right? The vector does not change its direction, right? It is only scaling its direction, right? It's just becoming bigger or shorter, right? Let's take another example. Let's take 1, 0 as an example, right? If you take 1, 0, let's say 0, 1, 2, 3 times 1, 0, this will be 2, 0. This is 2 times 1, 0. You can see that, right? So if you take 1, 0, then the 1, 0 vector is only scaling in its direction, right? Which means that this 1, 0 vector is along the x-axis. And if you do the math, you will see that it's the same case with 0, 1 also. So for this matrix 2, 0, 0, 3, the eigenvectors are 1, 0, and 0, 1. So what does this eigenequation? What is the eigenequation trying to determine? For any matrix, right? There are a bunch of vectors which are unaffected in direction because of this matrix. And what are those vectors? And right, and those vectors are called as eigenvectors. So the eigen decomposition is actually helping us to identify those vectors which are not impacted in direction by the given matrix. So that is the intuition, and we call these these vectors as eigenvectors. There are many synonyms for this: orthogonal basis vectors, right? The dominant directions, and there are many other things, right? So the eigenvalue decomposition is helping us determine these vectors. That's what eigenequation is trying to do, right? So the next question is like, why is this important, right? Why is this important, right? I think understanding these vectors will help us characterize the data better. And that's why it's important to identify these directions. I'll give you a simple example. Let's say that I'm giving you sambar, lentil soup.
Sorry,
Okay.
just before that. So when you say characterize the data, do you mean characterize the data as represented by the matrix? Is that what you mean? When
Yes,
you say
yes, yes.
Okay. All right.
Yeah. So there is a connection between going from data points to matrix, right? So that we'll do next after I give the intuition on why this is important. Okay.
Sure.
So that'll be covered in today's lecture. Okay. So I just want to take a simple example, right? So let's say that what's this? Okay. Let's say that I'm giving you a sambar or lentil soup. Okay. And then I'm asking you how the sambar tastes, right? Now we can look interpret sambar as in a 3-dimensional space. Okay. One dimension would be dal, right? The second dimension would be the lentil masala, sambar puri, right? And the third dimension would be salt. I am just oversimplifying it. Let's say that these are 3 dimensions for the lentil soup, right? Let us and when you're tasting the food, right? When you're tasting sambar, you're actually getting data in all these 3 dimensions. Okay. Let us say that I'm giving you a lentil soup without salt. Okay. So when you're tasting, your sensory system is actually sensing data in all these 3 dimensions, right? And then when I give you something without salt, it's only getting data in these 2 dimensions. That is dal and lentil masala. You see my point? So your brain is actually doing a eigenvalue analysis. It is identifying what are the dominant directions, right? What are the dominant characters for this particular lentil soup, right? And then it's trying to figure out, add data to different planes, right? When I'm giving you something without salt, right? The eigenvalue analysis is saying that the eigenvalue for salt is 0 because there is no data spreading in that direction, right? And but both for dal and lentil masala, you have eigenvalues which are not equal to 0.
So question.
And for salt,
so are we saying that salt, I mean, in your world, the intuitive world, salt, dal, and lentil masala are the eigenvectors here, right?
Exactly. Yes. Yes.
Okay.
Yes.
So
Exactly.
3 eigenvectors,
So these
3
are
eigenvalues, and then there'll be some data point where if it's terribly made sambar, then the eigenvalue against the eigenvector salt would be 0. That's what you're trying to say, correct? Okay.
Yes. Okay.
Right.
So bottom line is that is how our brain processes information. So what are we trying to do here, right? We're trying to characterize sambar, right? Characterize lentil soup, right? And we're trying to characterize lentil soup. What are we doing? We are only looking for like dominant directions, right? And that's how we interpret it, right? So this can be interpreted as like our brain doing some eigenvalue analysis, and that's how we instinctively process the data, right? So let's say that I'm taking you to restaurant, right? And giving you some exotic food XYZ, right? So what do you do? So in the previous case, I'm giving you a food where you know the eigenvectors that you need to expect, right? So you kind of know, right? I'm giving you sambar, so these are the dominant directions, right? and you're just estimating the eigenvalues, right? Now, let's say I'm giving you food that you have not tasted before. So what do you do, right? If you look at how your brain processes information, it's exactly the same thing, right? You look for dominant directions. So is this thing made of wheat or rice or whatever, right? That's maybe one direction, right? Next things could be simple as, is it sweet or is it savory, right? And the third dimension could be something else, right? So basically, you kind of increase the number of dimensions in which you process the data. In this case, you are trying to identify the principal components. You're trying to identify the dominant directions, right? And then you're trying to figure out like where the data is being spread. And that's how we characterize this food. You see my point? So this is how we fundamentally analyze data. That's how our brain intuitively works. And using the tools of mathematics, we are modeling that in a more rigorous fashion. And that's why this analysis is very, very important. Is that clear, guys?
Loud and clear.
Okay, cool. Okay, so that's the motivation here. So now we talked about eigenequation, which says, okay, we are given a matrix, we'll find the dominant directions using eigenvalue decomposition. And then we have seen why the dominant directions are important. So there is a missing piece now, right? So given a bunch of data points, I have to convert this set of data points into a matrix, right? So that is the missing piece now. Let me save this.
A question.
Yeah.
So if you look at the eigenequation, it's AV is equal to lambda V. Does that mean, of course, A comes from the data. How about V?
V is what eigenvalue decomposition will estimate for you.
Okay, so that's the eigenvector. The V.
Vector, yes.
V. All right. Okay. So though from a equation standpoint, we're defining it as a variable. I mean, when I say variable, I mean something that has to be estimated or figured out. At the end, I will get a bunch of vectors that satisfies this equation, right?
Yes.
Okay. Okay. I get it. Okay.
Yes.
Yeah.
Okay.
So as far as inputs is concerned, all that I need is A, nothing else.
Yes. Yes.
All right. Okay.
So why do you need that V? That's what I'm explaining. So
yeah. Right.
eigenvalue tells that, right? So I'm not going to the math of that V, how to estimate the V. I'm telling why that is important, right? Let's start this one. Is that the next one? Yeah, how do we get from vectors to, okay.
I think from data to matrix, right? That's what you wanted to talk about.
Yeah, data to matrix. From data to matrix. Let's say I have a bunch of points. Okay. So we know that if we capture these properties of these points in the matrix A, we can find the dominant directions, right? So it is, so if you from the intuitive explanation of eigen vectors, you mentioned that these vectors capture the scattering of data, right? So in which direction the data is spread, right? So obviously, if you want to convert these data points to a matrix, the matrix should capture the extent of scatter. Does that make sense? So this matrix.
Okay, correct me if I'm wrong. So let's say I just pick the bottom 2 points, then it's not going to capture the extent of the scatter, right? Because it's more horizontal. The bottom 2 points on your screen. So is that what you're saying? You know, it has to. I mean, as you rightly said, in this particular case, the scatter is perhaps in all directions. So I would need to capture data points from all directions, right? Okay.
Exactly, right? So a simple example, right? Let's take a circle example, right? That's why I gave simple examples in the previous video. I'm not sure how many people watched it. So if you look at, let's say that the data is generated on the circle, right? So you know that in both x and y directions, the maximum distance to the points is just r because it comes from the radius of the circle, right? Instead, if I use an ellipse, right, you know that on the x-axis, the maximum distance will be a, the major axis, right? And then on the y-axis, the maximum distance will be b, the minor axis, right? So in a sense, the major axis and the minor axis will capture the data that is spread on this ellipse. Does that make sense? Right? So here we have some nice parametric forms like ellipse and circle, right? But the data, if you get data from the real world, right, it's not going to nicely fit into this, right? So we still need a way to capture the properties of these into a matrix, right? So and if you want to do eigenvalue analysis based on the intuition, we know that the matrix should capture the extent of the scatter of the data, right? So how do we build this, right? So there are concepts called as moments of a distribution. Okay, so there are first order moments, second order moments, it keeps going on, nth order moments, right? So what is a first order moment? First order moment, let's just take a 1D data as an example, right? Let's say there are a bunch of points xi, okay, p is equal to xi. First order moment is nothing but the mean. Mu is equal to sigma is equal to 1 to n xi. It's just basically the arithmetic mean. This is giving you the average. When you say the average, what is it doing? Say if the data is like spread out like this arithmetic mean will actually give you a good sense of where the data is centered because you're averaging all the points, right? So this is the first order characterization of the data. It's just telling you, okay, I have a bunch of data points. I know that the data points are centered here. That's the first order moment, okay? The second order moment is the variance.
Right.
Yeah, variance. Variance is equal to, again, 1 by n, I is equal to 1 to n, xi minus mu, the whole square, right? So what is xi minus mu, the whole square? Xi minus mu, the whole square is this distance to the mean, right? I mean, square distance to the mean. Does it make sense, guys?
Yeah.
Right? So it is you're basically taking the square distance to the mean and then you're averaging it. That is what variance is. Intuitively, it is telling you the average distance of the points to where the distribution is centered, right? So intuitively, it's capturing the scatter, amount of scatter of the data. Does that make sense, guys? That's how intuitively you can understand variance, right? So now you can see how this is fitting into the expected properties of the matrix that we want, right? So you can use a variance as a measure of like how scattered the data is in different directions, right? Are these two moments sufficient to entirely capture the distribution, character distribution? No, right? So there are higher order moments. The third order moment is called as Q. The fourth order moment is called as kurtosis, and there are like multiple higher order moments, right? And people who are mathematically inclined, they can go deeper into all of this. But the first order moment and second order moments do provide good insights about the data. And for most practical purposes, these two moments are actually sufficient. Any questions on this?
No, my only question is how are these used?
Yeah, I'll go to that next. So I'm just giving you a 1D example.
Yeah.
Let's just see how it goes into the matrix. Okay.
So is it correct to understand, Arvind, that the moments or the ones that we are calculating here helps us determine the shape of our data.
Yes. I mean, the shape, again, skew is also a shape. So if the data is distributed like this, right? Sorry, if the data is distributed like this, right? Then the variance will not capture
this is like the fat tails, isn't it? Right? The skew.
Exactly. Yeah. So variance will not give you the exact characterization of this data, right? That's when you have to go to skew, and then the higher order moment is like kurtosis, like so many other things that you just keep going down the order, right? But 1 and 2, the first and second order moments, generally captures, at least for the simple problems, it'll capture the data distribution very well. And it'll help us identify, I mean, at least it'll help us identify downward directions very quickly. So for practical purposes, first and second order ones are simplified. And then even if you want to get into theory, approximating just based on first and second order moments will actually simplify a lot of derivations. So that's why people typically stick to these two. So in my work, I've not gone beyond second order so far. So so yeah, it's more like if you get deep into applied math, then
I'm glad.
yeah. So for engineering, this is more than sufficient. So that's what I feel. Okay. So I've just given an intuitive explanation of what variance is. We still have to go get into this matrix, right? So to get into this matrix, we have to go to higher dimensions. Let's take the second let's take a 2D example. Right? This, let's say this is the x vector, right? It's x and y, right? Let's do the mean again, right? 1 by n I is equal to 1 to n sigma or xi. So this is going to give you a x mu, y mu, right? Again, this will be 2 by 1. Let's do variance, right? 1 by n sigma I is equal to 1 to n. The square operation is implemented as
A transpose, is it? Product
transpose.
Right.
Right? It's a transpose, right? So this will be 2 by 1, and this will be 1 by 2. When you multiply it, what do you get?
2 by 2.
You see? Yeah. Right? So what does variance capture? The spread of the data, right? And what do we have here? A nice square matrix. So now it's obvious which matrix is A, right?
Sorry, why do you say it's obvious which matrix is A?
What are the properties of A? What is the expected property of A?
Should it be a square matrix?
No.
Oh, yeah,
For eigenvalue analysis, it should be a square matrix.
It should capture the extent, but how do we?
Yeah.
No, but when you were so categorical in saying that, I mean, if you just scroll down, can you? Yeah, you're categorical in saying that this is the, I mean, this matrix 2 cross 2 is A, and not 2 cross 1.
Yes.
What's the reasoning behind it?
2 cross 1, this is the mean first order moment, right?
Right.
So 2 cross 1, what does the mean do? It just tells you where the data is centered. Does it tell you about the extent of the scatter of the data?
No, certainly not.
What does variance tell you? It just gives you the square distances, right? So if the points are spread farther and farther, then it's going to reflect upon in the variance. Right?
Okay.
And for a 2D case, when you do that, it's giving you it's giving you a matrix. And this matrix is actually representative of the scatter of the data. right? And what is the expected property for doing eigen decomposition? We are saying that the matrix should capture the extent of the scatter of the data, right? If I'm able to do that, then I can do the dominant directions, right? So when we estimate, I mean, here it is called as covariance, not variance. For 2 plus higher dimensions, I'll tell you why. But is this intuition clear? I mean, I'm happy to pause here and take questions. Let's spend some time on this.
This expression, the covariance expression, I mean, we all understand it in 1D, but how does it come about in 2D? Xi minus mu times.
Okay. Sure. So let me then expand on covariance, right? Let's say xi minus mu is represented as xy transpose. Let's say this is xy like this. Okay. Now let's do this math. Xy times xy. That's what it is, right? Are we clear on this?
No, sorry, I didn't get this. So xi minus mu is equal to the one above. I didn't quite understand that bit. Say that again.
Let me write. I think let me write in right rotation, so that's easier. Let me write down the equation once again. So you know that it's sigma over I xi minus mu times xi minus mu transpose, right? This is the equation for variance, right?
That's my question. Yeah, my fundamental question is that we understand that in 1 dimension, where it's simply if I have xi, and I mean, if the, by the way, is this xi minus mu, and is that xi again, or is that a yi?
Xi. Okay, let me just go back and then start once again. In 2 dimensions, let's call it as x hat. X hat is x comma y. Are we clear on this?
Yep.
Okay. Let's look at the variance equation. Variance is equal to sigma over I. I'm just ignoring the by end part, right? So xi minus mu, the whole square, right? This is for 1 dimensions. Okay.
Correct.
I'm saying covariance is equal to, in 2 dimensions, sigma over I. I'm just moving to x hat. Okay. So now in 1 dimension, xi is a scalar, right? In 2 dimensions, I'm going to x hat, which is a vector. Are we clear on that?
Yes.
And mu hat, I'm just,
which is again
mu hat
vector,
is, I'm
another
just vector, right? So sorry, xi hat. So xi hat minus mu I hat transpose. Are we clear on this? Not mu I, sorry, mu.
That's.
Oops, it's too big. Are we clear on this?
Of course, the question is why transpose, right?
Y transpose.
I know this is what we do, but why do we put a transpose?
Yeah, I will tell you. Why. I'll give you the intuitive example, right? So you can, if you want the mathematical proof, I don't know, I have to read up. But
no, not
I can
that.
again give you.
Of course, not the mathematical proof, but why transpose
I will tell
intuitively, right?
Yeah, sure. So it's capturing the variance. One property of covariance is that it also captures the correlation. So how x and y are correlated, and let's see how this equation helps us achieve that. Okay. I'm going to simplify this as xy now. Okay, or if it's confusing, if you want to use something else, how can we do it? I think this is good, right?
This is right. This is right. I understand. We understand that. Yeah.
Okay. Let's do the multiplication now. This is what we're doing, right?
Right.
X square
plus
xy
xy x yx y square.
right? So if you take X as a 1D example, right? Look at the diagonal elements. This is the first dimension. It's capturing the variance in the dimension. The second dimension along the diagonal, it's capturing the variance in that dimension, right? If you look at the off diagonal element, XY, it's a product of X and Y. So it is telling us how X and Y are related, correlated, okay? And then same thing with Y and X. So to understand the concept of correlation, let's take a data, some data points as example, right? Let's say I'm taking these 3 points, 3, 0, 4, 0, and 5, 0, right? It is obvious to see that this XY product will always be 0, right? Some positive value, some positive value. This will be 0, this will be 0. Why? That's because the Y coordinate is always 0, right? Just by looking at this data intuitively, you can understand that Y is undisturbed no matter what X is.
Explain
that
in
clear?
this, sorry, in this context, I didn't understand. Say that again. Why are we saying that?
X is always 0, but Y is 3, 4, 5. So irrespective of what X is, Y is always 0.
Sorry,
Is
3,
this,
0, 4, 0, 5, 0. What are those?
these are data points.
Okay, all right.
Excise. I'm giving you the 3 data points, right?
Okay.
I'm just trying to explain how the covariance matrix will look like for these data points.
Okay. So Y is 0
right?
here, right? Not X.
Y is 0 here.
Okay.
Yeah.
Right.
Y is 0. So if you do this product and summation, this quantity will always be 0 because there's Y involved, right?
Right.
So the correlation will be 0. These elements will be 0. So why is it 0, right? So what does it mean? It means if you look into the data, right, you can see that Y is 0 for all 3 points, but X is varying, right? So what does it mean? Y is undisturbed by what X is intuitively. There is no correlation between X and Y. And that's why the correlation coefficients are 0 here. If you do this X minus mu and X minus mu transpose, you capture these things well. You get these product terms, right? And these product terms will tell you, it give you a measure of the correlation. You see my point?
Yep.
And if you extend to higher dimensions, right, you will see terms like this: X square, XY, XZ. Okay. And then again, there'll be Y square, YZ. This will be YX. So all the diagonal elements will be the variance in the dominant directions. And the non-diagonal elements will tell you the correlation between the corresponding dimensions.
So this
Is that
matrix
clear?
will always be a square matrix, isn't it?
Yes.
With the diagonals being the variance and off diagonal elements being the covariance, is it?
Yes.
All right. Okay.
You see the intuition here?
Right.
So
And
yeah. Go ahead.
Isn't the diagonal kind of symmetrical? It kind of reflects in a way because X, Y, YX, they kind of.
Yes.
All right. Okay. That too.
Yes.
Right.
It's a symmetric matrix. It will be a symmetric matrix.
Okay. All right.
It will be a symmetric matrix. Okay. So I hope I answered your questions, right? So where are we? We have gone from data to matrix. The matrix is actually capturing the properties of the scatter of the distribution in some sense. Okay. And
I have a question here. So does that mean any data set I get, my starting point to determine the eigen vectors would be to figure out this covariance matrix, is it?
Yes.
Always.
Yes.
Okay, because that's the one that tells us the spread of the data. Okay.
Yes.
All right. Got it. So
okay.
that's like a thumb rule, is it? And just curious.
Yes. Yeah. You need a matrix, right? So how do you go from data points to matrix? So this is
the matrix that is used in the engineering world.
Yes.
Okay.
Yeah.
Good. Got it.
So
because I've seen this at so many places But I've always wondered, why it is always, what is so magical about this particular matrix. So I've seen that, in a lot of places. Okay, now I get it.
Yeah. So this is all like highly intuitive explanations. I mean, if you want to go into the math, even I have to study.
No.
I mean,
Let's
like
people here are
yeah,
not particularly interested in the math. I mean, as long as
yeah.
we know what we
No,
are
but
doing, it's good for a start.
yeah,
Right.
exactly. No, but the funny thing is that unless you really go into the math and really bang your head hard, it's very hard to develop the intuition.
Yeah, I agree. I agree.
Right. So that's how I got the intuition myself, after a lot of struggle. I'm just trying to condense it as much as possible. So, okay, where are we here?
Oh, we were in the matrix,
Okay.
2 cross 2. Yeah.
Okay. Now, is this intuition clear? This part.
Yeah.
It's clear, right?
It is.
It's
At
obvious
least
that
I'm interpreting it as you've come up with
yeah.
a nice magical matrix comprising of variances and covariances, and that's the one that we're going to use to determine the eigenvectors. Right?
Yeah. Yeah.
Okay. Got it.
Okay. What was the next in the agenda?
You had the agenda with you? I think you had.
Data points and understanding covariance matrix. Oh, okay. So finally putting everything together, understanding dimensionality reduction. Okay. Okay, let's go to.
You've already touched upon covariance matrices, right? Matrices, right?
Yeah. That's done already. Yeah.
Right.
Okay, now dimensionality reduction, right? How are we on time? We started at 9.
We have a hard stop at 12:30 India time. Does that sound okay? Another 45 minutes.
45 minutes is more than sufficient. Yeah.
All right. Thank you.
So I was just trying to give some intuition, right? Previously, let's say if the points are spread along these directions, right? The dominant directions will be the x-axis and the y-axis, right? So let's just bring our understanding of covariance matrix here, right? So if you look at these points, right? This will be either x0 or 0y, right? Because they are aligned along the x-axis and the y-axis, right? So which means that the covariance matrix will be of the form some sigma 1 square, sigma 2 square, 0, 0. Are you guys clear on this?
Because the product will be 0, right? The product of x and y.
The product will be 0, right? So looking at this covariance matrix, you can tell that there is no correlation between x and y, right? And there's some scatter in the x direction and some scatter in the y direction, right?
Sorry, just one question there. So when you're calculating covariance matrix, I just want to be absolutely sure. Do we take data pairwise? And then no, we don't, right?
This is the equation.
Oh, okay. Right. So when
how
we say
far
sigma,
data is from the mean?
Okay. So when we say sigma 1 square, we just take all the x values and then compute the variance. Is that right?
No, if you do this math, if you do this math, you will get some non-positive, non-negative values along the diagonal. I'm just calling that. Okay, if it's confusing, let's just name it as A and B. Some non-negative values along the diagonal, A and B. Is that clear?
No, what I want to understand is what is A? Can we say A is nothing but the variance of
Yes.
The variance along
yes.
x direction in this particular
Yes.
case, right?
Yes. Yes.
So I take all the x coordinates. Since we're talking of 2D, I think we're comfortable with coordinates in the Cartesian plane, of course. So I'll take the x coordinates and then compute the variance. Is that A?
You just implement this equation, and what you end up getting here is that. Why? Because if you look at the, if I'm just taking x and y, I'm multiplying, but what I'm getting here, I'm getting x square. That's what you end up getting.
Okay, all right.
Right?
Okay.
So yeah, if I take points only on this plane, right? On the x-axis and y-axis, it's obvious to see that, you know, the off-diagonal elements will all be 0, right? Best by looking at this matrix, I can say that, okay, the data is spread only along the x and y directions. So the dominant directions are nothing but x-axis and y-axis. So the corresponding eigenvectors will be 1, 0 and 0, 1. Is it clear? Now let me look into, let me just share the Google Colab I shared with you guys earlier. Let's just open it up. What's this? Do you guys name the name? Remember the name of the Google Sheet? I just forgot. What did I do? Recent. I think it's pca.pnb. I think this is the one. Yeah. Let's just execute this. Okay. Look at this. Okay. Can you guys see my screen?
Yep.
Okay. So I've considered some points only on the x-axis or the y-axis, right? The first step is I'm estimating the covariance here, right? And if you look at the covariance, you can see, right? You can see this is the variance along x and variance along y, and then the off-diagonal elements are all 0. Okay. Okay. And then I'm passing this matrix and then to the value decomposition, and then just plotting the values, eigenvectors and the values, right? You can see that the eigenvector 1 is 1, 0, which is along the x-axis, right? And then the eigenvector 2 is 0, 1 along the y-axis, right? And you can see that the eigenvalues are 16 and 16. Don't worry too much about the exact values here, but you can see that both x and y eigenvalues are exactly the same. The reason being, it's 5 and minus 5 in both for both x and y. So the amount of scatter is exactly the same. And that's why you're seeing the eigenvalues to be same. Okay. And then I'm just plotting the eigenvectors. You can see that those are orthogonal. Okay. This is the first data. So now I want to change.
A question. Eigenvectors are always orthogonal, is it?
Yes.
So by that, do we mean the dot product will be 0?
Dot product will be 0 and the angle between the vectors is 90 degrees. If the dot product is 0, and that's what you see.
A question. What's the difference between orthogonal and orthonormal?
Orthogonal vectors which have unit norm are called as orthonormal.
Oh, all right. Okay.
So yeah, you just have to look at the magnitude of those vectors. That's it.
All right. Okay.
What did I do here? So this is good. This is a circle. I think I lost one example, which is along the line. Okay, again, let's go for this circle example, right? I generated points on the circle. Again, what you can see here is the first eigenvector is 1, 0. So 5.7 times 10 power minus 16 is literally 0, right? And then again, the eigenvector 2 is 0, 1 because there is no correlation between the x and y data points here. And then you can see that the eigenvalues are again 2 and 2, approximately 2. The reason being they're actually equally spread in both directions. Okay, now let's look at why is this, where is the ellipse is here. Ellipse is here. So I'm changing the major axis and minor axis, right? It's basic. You can look at ellipse as a squished circle, right? Now I'm saying that the major axis is twice as big as the minor axis. So the data will be spread around like this, right? Now, if you do the eigenvalue analysis, you can see that along x-axis, the eigenvalue is 2, right? And along y-axis, you cannot say it's x and y-axis along the first dominant direction, along the second dominant direction. That's how you should say it, because if the data is rotated, the eigenvalue will still do the same thing, right? Analysis will figure out the same values. So you can see that this eigenvalues are actually giving you an idea of the scatter of the distribution. You can see that, right? The eigenvalues are changing, but then the eigenvectors are not changing. It is still 1, 0 and 0, 1. You see my point? That is because if you look at the covariance matrix above, the off diagonal elements are still 0. So it's 10 power minus 17 and 10 power minus 17. So this covariance matrix is still capturing the scatter of the distribution. You see your point? And the eigenvector is saying that the eigenvectors have not changed, but I know that the data has actually spread in spread to a different extent. The covariance matrix is capturing that, and the eigenvector values are implicitly telling us that. You see? This example is not working well, so I'm going to skip. I'm yet to figure it out, but I will tell you an example that is working very well. So this is a Gaussian data. You can again interpret this Gaussian data as like an ellipse, right? But not a perfect ellipse. But here the difference is that the ellipse is rotated. You see, it's not axis aligned, right? And if you look at the covariance matrix, it is actually reflecting in the covariance matrix. So you can see that the off diagonal elements are not 0. Okay. And then I do the eigenvalue analysis. I'm plotting the eigenvectors here. Let's focus on that first. You can see now that the eigenvectors are not aligned across the x and y directions. It is actually aligning across the direction of the data spread. You see my point? That's what eigenanalysis is saying. Eigenanalysis is saying, see, these are the dominant directions in the data. The previous examples, we were just constructing examples that were axis aligned. Now I'm just rotating it, and then I'm just saying find the eigenvectors, and then eigenvectors is saying, oh, see, this is where the data is actually aligned, right? And then correspondingly, you can see that no, it reflects in the eigenvectors. They are not 1, 0 and 0, 1 anymore, right? And it's saying that in the first dominant direction, it's 6.7, and the second dominant direction is 3.0. So basically, what we are saying is that in the first dominant direction, the data is spread at least twice as much as the second direction, right? So and we are dealing with 2D examples, so we can visualize. Once you get greater than 3D, we cannot really visualize, and that's where these tools are really useful. You see your point? Any questions?
I have one thing. Let's say the covariance calculates the spread of the whole data, where the eigenvectors calculates the spread of each features in the data. Can we interpret in that way?
the covariance matrix captures the correlation
Spread of-
also, right? Right?
Yeah, which means like
So
how much.
eigenvectors,
Mhm.
yeah, the eigenvectors will tell us, okay, these are dominant directions in the data. So if you rotate your x and y to these eigenvectors, then the correlation becomes 0. Is that clear? Let us see what is the difference between this data here and the circle data before, or the ellipse. Let's take this ellipse data here, right? So if I do this ellipse data, what's happening? The eigenvectors are around x and y, and the corresponding off diagonal elements are 0, which means that there is no correlation, right?
Yep.
But here there is some correlation, but then eigenvectors are along this direction. Let us say that you're actually rotating x and y axis along the direction of this eigenvectors.
Then 0 correlation.
Then there'll be 0 correlation. So those are dominant directions, right? So to take the example of like salt and dal, right? They're like orthogonal directions, right? One is not related to the other at all. And eigenvectors give you the directions, gives you such directions in the data. If I project all the data into these vectors, then I know that those are there is no correlation, and those are the independent directions. Does that make sense?
Yeah. So technically, you need not include the entire features in it. So you need only the dominant direction, so that you like whatever the computation you do, it is like not that heavy as compared to the original features what you have.
All I'm saying is that if you take the xy and project it onto these eigenvectors, it will give you a new. Let me just draw. I think drawing is easier. So now we have. Oh, let it stop. Okay. So now the data is spread like this, and each data has this x and y coordinate, right? Right?
Yep.
Now I'm saying this is the eigenvector.
Sorry, one
These are the
part is
eigenvectors.
not
I think
visible.
your collab screen overlaps your diagram. Yeah.
Okay. Okay. So what I was saying here is that these are the points, right? Let me just start from the beginning then. That's easier. Let's say the data is spread like this. And each of these points will have an x and will have an y. Right?
Yeah.
Right? And this is x and y is along these eigenvectors 1, 0 and 0, 1. I mean, by default, we assume that the x and y axis is orthogonal. So by default, those are default eigenvectors. That's how we can look at it, right? After I do the eigenvalue analysis, I am saying that these are the eigenvectors, which means that these are the new x's and y's. You see my point?
Yep.
And if I project, so what is the x and y in this? What are the coordinates of these points on this new coordinate frame? I can project this point here and get this x, and can project this point here and then get this y, right? If I do this projections and move into this new space, which actually represents the dominant directions of the data, then it is equivalent to forming a new ellipse in this eigenvector space.
Got it.
Does this make sense?
Yeah, much more. Yeah.
Right?
Yeah.
Right? So once I do this, and if I compute the covariance matrix, what do you think the covariance matrix will be?
Like orthogonally, there will be value, and like non-orthogonal, everything will be 0 because there won't be any.
And diagonal, yes. So you see, in a sense, you're saying that okay, although so when we enter the data, we think this is x, this is y, but actually that's not the actual x and y for data.
Makes sense. Yeah.
You see my point? So that's what is eigenvectors is doing for you.
So how? Okay, let's say okay, makes sense. Yeah.
Okay. So where was I going with all this? I totally forgot. Okay, we are doing this eigenvalue.
Dimensionality reduction, is that what?
Yes, yeah.
Okay.
Yeah, so finally dimensional reduction. I think for dimensional reduction, let me just go with the example XY. So any more questions on this, guys? Is this intuition clear?
This is good.
Okay. We have seen nice examples of data scattering all over the place. Now I want to consider this example of points on this line. This line equation is x is equal to y. Okay. Now let's look at the covariance matrix for this. Okay. We are doing x, y times x. No, other way around. Sorry. Okay, let's write it here. It's x, y. This is the covariance matrix, right? X, y transpose, right? Let's expand it. So x square, x, y, yx, y square, right? This is the covariance matrix, right? But we do know that x is equal to y because this data is coming from this line equation x is equal to 5, right? So let's just plug that here. What does it say? X square, x square, x square, x square, right? So which just by looking at this covariance matrix, you can tell that I know everything about this data just by looking at one dimension. Is that clear?
Yep, agree.
1, 1, 2, 2, 3, 3, 4, 4, right? Just by looking at one dimension, I know everything about the second dimension. So do I need two dimensions to represent this data?
No.
That's the intuition behind dimensional reduction. You see my point?
Yeah.
So now the question is, how do I determine this direction, right? Again, if you look at this intuitively, there is only one dominant direction, right? So that is this direction. Okay. If I feed this data into the eigenvalue analysis, what do you think the first eigenvector will be?
1, 1.
Exactly. It's scaled version of it. Basically, what I'm saying is the x and y coordinates will be the same. It's just the direction, right? The second direction will be?
Difficult to say.
4, 4.
No, it has to be
4, 4 is still the same direction as 1, 1,
Okay.
right?
Minus,
So minus
1 and 1. Something
yeah,
like that.
or 1, 1 minus 1 also.
Yeah,
that will also be a direction.
Right.
Both are the same only because AV is equal to lambda V. A of minus V is equal to lambda of minus V, which still implies AV is equal to lambda V. So V is an eigenvector, minus V is also an eigenvector. So that's simple algebra. Right. So, okay. What would be the, can you comment on the eigenvalues for this?
1, and the other one will be 0.
There's some positive quantity for this.
Yeah. Some positive. Positive K, and the other one will be 0.
Another one will be 0, right? So by looking at the eigen values, you can tell, right? The data is actually spread only in one direction. So in this 2D example, I've drawn a line so you can see it, right? It's also obvious from the covariance matrix, but if you do the eigenvalue analysis, you know that just like the lentil soup example, right? One eigenvalue is 0, so it tells you that, data is spread only in one dimension, right? So now if you extend it to like multiple dimensions, right? Typically we deal with dimensions like in thousands, right? That's what we deal with. You really want to know when all those dimensions make sense, right? Maybe that's the simplest a set of dimensions that best characterizes the data, right? And probably projecting that to those simpler dimensions will help you clean up the data. It just tells you what the dominant directions are. So once you know that, you can actually do we can implement better algorithms on top of it. So is that intuition clear? That's why we need to do dimensionality reduction. You see my point?
Just a question.
Yeah.
Practically, what sort of reductions have you seen? From how many dimensions to how many?
So to be honest, this dimensional reduction is not, we don't really do in the context of compression. So compression is mostly an example, and I mean it's also because I've not worked much on compression, right? So what we are interested in doing is that, at least from robotics context, we try to understand the matrix, right? So if one of the eigenvalues are 0, then we know that the matrix is rank deficient. It's not spread in all directions. So it's actually, when you try to do that, use that in any solvers, then we know that the determinant will be close to 0, and we have to interpret the results accordingly, because we know that there can be some numerical instabilities and stuff. So and purely in terms of like reducing number of dimensions in the data, I've not worked on such applications, so it's hard for me to comment on that.
All right.
But the intuition is still the same. You need to understand, okay, is this matrix really capturing data properly? Can I use it in algorithms or not? So that's the intuition. Right. Yeah. So so eigenvalue 0. Yeah. That's the intuition behind dimensionality reduction. Any questions on this, folks?
I'm good.
Okay. Are there any other questions that other guys have? I think we have covered most of the topics, right? I think we covered all the topics for today, right?
Yes, we have.
Okay.
Others, any questions? I think those who had questions.
VC, I do have a question.
Oh, go ahead, somebody.
Yes. So let us take like we do have two axes, x and y. Let us assume like x is time and y is speed, just an assumption. Okay. So now we have after dimensionality reduction, so we got a new axis. Okay. So this axis will be just a combination of if we take like speed and time, it may be a combination of these two, right? So similarly for multi dimensions, like if we go for like 4 or 5 dimension, so it may be the combination of like 2 or 3 components. Am I right? Is it that way?
Yes, yes. So the way to interpret this data here, let's consider this example, right? Right. All I am saying is the new dimension is 0.73 times the first dimension, minus 0.68 times the second dimension. That is what it is. So when you actually feed the data, right? So our data will be in some will have some semantic meaning, right? So if you look at age versus height versus sex as a data set, right? So age is basically x-axis, right? So x has a semantic meaning. Y is maybe sex and whatever that is, right? When you do an eigenanalysis on that data, then you'll get a vector like this. So what does this vector mean? It means that it's 0.73 times age and minus 0.6 times the sex, right? That's what it means. So once you go into this eigenvectors, you'll get new dimensions, but the dimensions will lose their semantic meaning. Does that make sense?
Yeah, it makes
so by
sense.
that when you say it will lose the semantic meaning, what you're trying to say is, I mean, as a domain expert, I may not be able to interpret what that exactly means or why that number throws up, something like that, right?
Exactly. Yeah, that is exactly why it's hard to explain why a machine learning algorithm isn't working, right? That's the problem. That's the general problem with ML algorithms. So why were I mean, to give you a bit of history, right? In the 80s, late 80s, neural networks were really big, right? And then it got killed in the early 90s due to some reasons. And most of the credit card companies were using neural nets in late 80s in the US. But in the early 90s, they all switched to decision trees. This is a history that was told to me by one of my professors. And one of the main reasons was that in decision trees, at each node, you have some dimension, right? That's a human readable dimension. So if a credit card company is actually rejecting a credit card application, so through the decision tree, you can actually find a semantic meaning to the decision. You see your point? You can say that, okay, in this node, this is the threshold, and this node, this is the threshold, and that's why we rejected you. But if you try to get into other techniques, right, neural nets as an example, you lose all the semantic meaning, and you cannot really explain why you made a particular decision. And this is like more of a history, right? So this is why apparently neural networks were not favored in the early 90s, and most credit card companies use decision trees. So
interesting.
Yeah, I don't know how true it is, but somebody told me. But it kind of
I think it makes sense, a lot of sense, because finally, after doing all this, you'll have to sell the algorithm too. You know, the way the algorithm works. That's important too, right? You just can't say it's magic.
Exactly.
That won't sell, right? Okay.
Yeah, but that things have changed. We are still doing neural nets, and nobody's asking why. And if we cannot ask why, it is what it is. So,
I mean, is that because of the number of parameters? We're dealing with millions and billions of parameters, right?
Yes. Yeah.
So there's nothing that you can say, you know why it works. It just they'll say it works. That's it, right?
Yes. Yeah.
Understand. Sabari, was your question answered?
Yes, it was answered. Now I'm clear.
So Arvind, which means these new dimensions are like a linear combination of the original dimensions, is it?
Yes, that's what it is.
Oh, okay. All right. But it's just that the combination, the exact linear combination may not make sense to us. May not. Why it is so is okay. All right.
Yeah.
Any other question, folks? Those on the call? Okay, I shall take that as none. If there aren't anything else, thank you, Arvind, for a wonderful session. Hope to see more of this in future. Thank you.
Yeah, definitely. Yeah, whenever I have time, I can chime in. Yeah.
Oh, please. Thank you. Thank you very much. Bye.
Bye. See you guys.
Thank you.
Thank you, Arun.